Hello everyone. In this portion of the course, we're examining key aspects of the science underpinning e-flows. Last week we focused on hydrology, and this week we're focusing on hydraulics and geomorphology. At the beginning of this lecture on basic channel hydraulics for e-flows, I'd like to acknowledge Dr. Lindsay Beavers of Heriot-Watt University in Scotland. Lindsay used to teach the hydraulics portion of this course, and some of her influence remains in what I'll present today. The distinction between hydrology as reflected in discharge and hydraulics is clear in this photo. At the instant the photo was taken, discharge along this river was more or less equal at every cross-section one could measure, but it's plain to see that hydraulic conditions in the river were not equal. The river emerges from the bottom of the photo, flowing through a bend to the left and then to the right. Where it appears the flow is smooth but differs from left where it is shallow and slow to right where it's deep and fast. As the river turns to the left, the slope increases and the smooth flow is disturbed and accelerates through the riffle. At the base of the riffle, flow again slows, becomes deeper, and turns gently to the right, ready to change again depending on downstream characteristics of slope and channel shape. Organisms living in the stream do not experience the hydrology. They experience the hydraulics. The river's morphology and bed sediment characteristics are also the product of hydraulic forces. These images show a fisherman's view of the river, which understandably tries to see the fish's view. For the fish, the river is an interconnected set of habitats defined by different depths, flow velocities, and substrate types organized into riffles, rapids, glides, and pools. Eddies behind rocks provide resting spots, and fallen trees provide shelter. Vegetation along the river's margins also feels the changing moisture levels linked to the rise and fall of water depths, while discharge is the integrated whole of these small organism scale variations. Hydraulics is the fine-scale reality. So, if organisms and the ecological processes they are part of see the river from a hydraulics perspective, and hydrology is the integrated whole of the channel hydraulics, then hydraulics form the link between river ecology and hydrology. Birds, mammals, fish, amphibians, insects, and mollusks experience river hydraulics. Changing zones of vegetation from low to higher portions on the river banks experience river hydraulics. And geomorphic processes experience hydraulics, as we'll discuss more in the next lecture. But water is managed through the lens of hydrology in units of volume per time. So to preserve the requirements of ecosystems while managing volumes for multiple purposes, we must link these two worlds. The basic element of this linkage is the river cross-section. A cross-section is a two-dimensional view of the elevation profile perpendicular to the river channel. A full hydrologic cross-section includes both the river channel and its riparian and floodplain areas. The boundary between the river and its floodplain is referred to as bank full flow and can be characterized by a bank full width, bank full depth, and bank full wetted width. The hydrologic floodplain extends beyond the edge of the channel to the outer limit of the floodplain. Bank full flow, or stage, is a widely used standard for comparison among rivers and has been studied in thousands of rivers around the world. The discharge corresponding to bank full flow varies from river to river, but on average it's equivalent to a flow that's exceeded every 1.5 years. The dimensions of the channel and floodplain are clearly visible in this photograph of the Songkul River in Kyrgyzstan. Note that at the time of this photo, the river was not flowing at bank full flow, which is normal. Of course, cross-sections can be used to measure the width, depth, wetted width, velocity, and bed material of the flowing river under many conditions, and key habitats for river organisms and other ecologically relevant information can be mapped directly onto them. You'll remember the classification of flow levels shown on this image from an earlier lecture mentioning the approach to e-flows in the Murray-Darling Basin of Australia. It shows that base flows are sufficient to provide reliable habitat for a variety of stream organisms and inundate vegetation on the bench to the left. However, inundation of vegetation on higher benches, like that to the right, requires higher flows, termed freshes. And inundation of fringing wetlands only occurs as flows approach bankful levels. Even less frequent overbank flows are required to reach out onto the floodplain and inundate key floodplain species. All of these flow levels have their ecological purposes expressed in terms of depth, wetted width, velocity, and bed material, and hydraulic analysis of the cross-section enables us to translate these variables into specific flow levels expressed in cubic meters per second. Extension of this hydrologic analysis longitudinally along the river requires the delineation of multiple cross-sections and the mathematical representation of flows between them. These figures show on the left an example of a simple single cross-section within the hydraulic modeling software HEC-RAS, and on the right a series of cross-sections along a section of river. HEC-RAS is the river analysis system of the U.S. Army Corps of Engineers Hydraulic Engineering Center. It's a well-documented and freely available modeling system. HEC-RAS allows for a wide range of hydraulic analyses and is used for many purposes. In e-flow science and practice, it's commonly used to simulate the key hydraulic variables at cross-sections used in e-flow's assessments. You'll hear more about this tool when we reach the methods units, but I've included the HEC-RAS User's Manual among the additional reading materials this week for those of you who are eager to delve into it. As with the IHA software, you can download HEC-RAS to your computer and install it. I've included a link to the download site in the additional materials, and I've also included a link to a popular online tutorial introducing you to the basics of HEC-RAS. Let's take a moment to consider some fundamental aspects of hydraulics and approaches routinely taken to simplify the physics and focus only on the key variables we need for e-flow's assessments. Have a look at the photos along the bottom of this slide. They're all taken from the same point on the Mara River near the Kenya-Tanzania border. The photo on the left shows the Mara at low flow, while the photos in the middle and right show the river under increasing flow conditions. It's clear that the energy level in the river increases greatly with flow. It's becoming more turbulent, it's flowing faster, and waves are developing on its surface. Imagine how complex the physics of flow is in 3 dimensions in the river and how it's changing over time. On a theoretical level, physicists have identified the relevant forces underlying this complexity, as well as the relationships between these forces. The Navier-Stokes equations shown on the slide describe these relationships, but these equations have never been solved in all of their detail, and to be applied, they must be simplified and approximated using numerical methodologies. For our simple purposes in e-flow science and practice, we're mainly interested in quantifying the depth and velocity of a river for different discharge magnitudes at individual cross-sections. Solving for these 2 unknowns requires 2 equations, and those most commonly used are the conservation of mass equation and the momentum equation, which is derived from Newton's second law. Together, these are called the Venant equations, and they are the basis for one-dimensional modeling for hydraulic flow between cross-sections. They're partial differential equations in terms of distance along the channel, x, and time, t. We can use the conservation of mass equation to solve for depth, and the momentum equation to solve for velocity. But the momentum equation will need to be simplified further. The individual terms of the momentum equation are identified in the upper equation. They include the local acceleration term, the convective acceleration term, the pressure force term, the gravity force term, and the friction force term. In order to prepare for the eventual solution, in the middle equation, all terms have been divided by negative gravity, g, and the friction force has been added to both sides. Now, if we assume that the flow is steady and does not change with time, we can ignore the local acceleration term, which varies as a function of time. Similarly, if we assume that channel shape remains uniform, we can ignore the convective acceleration and pressure force terms, which vary as a function of x and y. At this point, the equation indicates that the bed friction is balanced by the gravity slope. If bed friction is balanced by the gravity slope, we're able to make use of two well-established equations to calculate velocity from hydraulic radius, slope, and a coefficient reflecting the roughness of the channel. The Manning formula is more commonly used in river hydraulic analyses because values for the coefficient have been empirically determined for many conditions, but the HEC formula, which is more theoretical, is also used. Hydraulic radius and slope are available from the cross-section data. HEC-RAS makes use of the basic theory just presented and information from the measured cross-sections to simulate water surface level and velocity along cross-sections. Water depth can be calculated by subtracting the bed level from the water surface level. The figure on this slide shows a comparison of simulated and measured surface level at a cross-section on the Mara River just downstream of the point of the three photos I showed in slide 9. Simulated and observed water levels are nearly identical in this example, and velocity is well simulated over much of the cross-section, but simulated velocity is higher than observed velocity on the right side of the cross-section. In general, however, this level of accuracy in hydraulic simulations is suitable for the purposes of translating flow volumes into depth, velocity, and wetted width, or vice versa. This is another example from farther downstream on the Mara River in Tanzania. Here, vegetation types and channel features important for insects and fish have been mapped onto the cross-section. During the eFlows assessment, ecologists were able to identify depths necessary to meet a number of ecological needs. These are shown in the boxes on the lower right. At the bottom, ecologists have indicated the depth needed to ensure survival of fish and insects during extreme low water periods. They will have also indicated a needed velocity, although this is not plotted. Deeper depths and increased velocities are needed to inundate sandbars and support insect reproduction. Still deeper depths are needed for seed dispersal and to enable migration of fish along the river at the correct times of year. High flows are needed occasionally to recharge riparian groundwater, and large floods are needed infrequently to maintain the shape of the channel and inundate the highest levels of riparian vegetation. Ecologists map these needs onto the cross-sections, and the hydraulic modeler is then able to translate the requirements for depth and velocity into discharge magnitudes that will provide them. In this lecture, I've mainly focused on simple, one-dimensional hydraulic simulations along individual cross-sections, and for many applications of eFlows, these are sufficient. But the computational power of modern computers, of course, allows for more detailed 2- and even 3-dimensional modeling of channel hydraulics. Delft 3D, developed by Deltares here in Delft, is a popular system for this type of modeling, and there are others as well. And now for the take-home messages of this lecture. Hydraulics provides the link between flow-related characteristics of ecological habitats and river discharge, and channel cross-sections are the place where these meet. These are mainly depth, velocity, and wetted width. Bed composition is also important, and you'll learn more about that in the next lecture. We saw that the physics of channel hydraulics is exceedingly complex, but with a number of reasonable assumptions and available analytical software, key hydraulic variables can be simulated with sufficient accuracy. Ecologically relevant channel features can be mapped directly onto cross-sections to facilitate the process of estimating e-flow levels and translating hydraulic needs into discharge magnitudes. Where needed, more sophisticated 2- and 3D simulations are also possible, but these require more computational power, time, expertise, and expense. They will have their place in highly sensitive or otherwise economically important settings, but in most cases, simpler hydraulic approaches should be sufficient. That's the end of this lecture. Thanks very much.